Well, hello again, everyone, and welcome to iChem. We are in our unit on um, kinetics and heat, and we're really on our section on kinetics. And last time we talked a little bit about what is the study of kinetics, and the study of kinetics is the study of reaction rates and reaction mechanisms. And we said, hey, a reaction mechanism is the step-by-step process that a reaction goes through, and that a reaction rate really is the change in concentration of a product or reactant over change in time, that is a reaction rate. And then we said, hey, let's talk about what a reaction really is. What must happen for a reaction to occur? The prereqs, you might say. What are the prerequisites for a reaction to occur? And we said we have to have collisions. We have to have proper orientation in these collisions. And what I mean by orientation, we have to have the molecules turn the right way, for instance. And we have to have sufficient energy. That if I don't have all three of these, I won't have a reaction occurring. So I need to have collisions, collisions with proper orientation, and collisions with proper or sufficient energy. And then I said, hey, what else do we have here? We can talk about what effects, if factors which have an effects on reaction rate, right? And we said, okay, one can be increasing concentration. If I increase concentration of the reactants, then I'm going to have more reactants available, meaning more collisions, more increase in reaction. I said I could increase my surface area of my reactants, and that's usually for solids. And by increasing surface area, then more of the solid particles are available to be hit by the other reactants. If I have more available for hits, more collisions, that means my reaction rate increases, right? Reaction rate increases, reaction rate increases. What else can I do? I can increase temp. If I increase temp, that means my velocity increases, and my velocity increases, that means I have more collisions, and more collisions with greater impact, so my reaction rate increases. And 4, I can add a catalyst. And a catalyst will increase my reaction rate, usually how? By lowering something called the activation energy. Good. And that's really where we left it last time. Now, we want to jump in to this kind of question here. Consider, what is the change in enthalpy? Change in enthalpy of a reaction, of enthalpy of reaction, sorry, for this reaction. Okay, what does this mean? I'm not sure. Well, we want to come over here and we want to talk about energy diagrams, which, yeah, is kind of a talk about kinetics. And part of this is we want to go back and review a little bit about heat, and we want to talk about heat of reaction, okay? Now, what is heat of reaction? Really, the heat of reaction is the difference between, the energy of the products minus the energy of the reactants. Now, that's not exactly the definition, but for us, for honors chem, we'll look at it that way. The energy of the products, meaning what's the total energy, potential energy we might want to go with, the potential energy that the products have minus the potential energy of the reactants. And we let that thing be represented by a delta H, and oftentimes we put delta H reaction, but not always. And the things that we need to understand here is we can have two outcomes. I can have delta H, which is less than 0, and I can have delta H for my reaction that is greater than 0. And when delta H of reaction is less than 0, what does that mean? That means it's negative. And if we go back to this, what does it mean if it's negative? That means if it's a negative value, that means my energy of the reactants is greater than the energy of the product. So this means energy of reactants is greater than energy of my products. And that number is a negative, and if that's the case, what has happened? The reactants have what? Given off energy, that means, which means this is an exothermic reaction. Got it? And we talked a little bit about exothermic. In this case, Where my delta H is positive, that means the energy of my products is greater than the energy of my reactants, and that means it is an endothermic reaction, right? If my products have more energy, that means they picked up energy during the reaction relative to the reactants. You get that? Or my reactants, as they are transformed into products, they gain energy. Got it? So that's an endothermic reaction. Okay, I think we can go back and answer this. What is the change in enthalpy of reaction? Well, to figure that out, we just look over at this thing to the right. When they put this number, this delta H, that means that is the change in enthalpy of this reaction. So what is it? It's negative 10.4 kilojoules. Ooh, piece of cake. Is this exothermic or endothermic? Well, I look at the sign. It is a negative value, so it is exothermic. Is heat released or consumed? Well, if it's a negative value, that means heat has gone from my reaction to what we call the surroundings. So that means heat is released. So during an exothermic reaction, heat is released. What does this imply about the energy of the products and reactants? Well, if heat is released, if this is a negative value, what does that mean? That means the energy of my reactants is greater than the energy of my products. Cool. All right. I think you guys can do this one then on your own. Bring me back when you're ready. What's the change in enthalpy? Easy. 226.8 kilojoules. Great. Is this exothermic or endothermic? Well, it's positive, so that means it is endothermic. Which has more? Well, that means what? My products, if it's a positive value, the energy of my products is greater than the energy of my reactants. Hey, this is a piece of cake, right? And think about that. We said that my delta H is equal to the energy of my reactants minus the energy of my, oh, excuse me, I had that wrong. Yoink. Energy of my products minus the energy of my reactants. If this number is positive, that means this number must be bigger than that number for me to have a positive value. Got it? All right, moving on. Zoink. What must happen to H2 before it can react with the I2? Okay, let's analyze this. I've got H2 plus I2, and it's going to yield 2HI. So let's think of this. Over here, I'm going to have a hydrogen, and that hydrogen is overlapping another hydrogen, right? So those are my two hydrogens. And I have a bigger molecule, and these are my two iodines. So let's put a little I there. Those are my two iodines. Now, what do I get over here? Eventually, I get what? A big iodine and a big iodine and a little hydrogen overlapping it and a little hydrogen overlapping it. Good. So now the question is, how do I get from this situation to this situation? Well, first thing is what? What has to happen to my hydrogens? My hydrogens have to what? Each hydrogen has to kind of separate from each other. Got it? What has to happen to my iodines? Each of my iodines has to separate from each other. So that means essentially I am breaking this bond and I am breaking that bond. Now, tell me, what happens when I break a bond? When I break a bond, what? Energy is consumed. It requires energy to break bonds. Ignore what your biology people say if they say otherwise. It's not true. Energy is required to break a bond. Think about if you have a magnet, which is a positive and a negative. What does it take for you to separate the magnet? It takes energy from you to separate the magnet. That means when the hydrogens separate, that is endothermic. And when the iodine separates, that is endothermic. Got it? And so that means what? I've had to put energy in to get to this position. This requires I have to add energy to get to this position. Then what starts happening? Then I start going this way, and as these bonds form, what happens? This is exothermic. forming bonds is exothermic. So both of these form bonds, and energy is what? Energy here is released. Okay. Release. No, how about release? There we go. Okay, and what must happen to the iodine? Yeah, we talked about both of those. So there's got to be some preparation. We've got to put some preparation into our reactants before they're in a position to become products. Got it? Now, draw the energy diagram. Okay, let's take a real quick note here on the energy diagram. I was talking about that here. And energy diagram. Zinc, 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 zinc. Coming down, give me some more space. Energy diagram. What is an energy diagram? So we want to talk about an energy diagram. It's this simple, folks. This is a diagram. This is really a diagram, not a plot necessarily, a diagram or a picture showing potential energy versus extent of reaction. And what do I mean by extent of reaction? Going from reactants, the development of a reactant becoming a product. As you go down that path, how does your potential energy for the atoms and molecules change? And it looks usually something like this. You've got potential energy. Sometimes they just say energy. And you have extent of reaction down here. And then you would say, okay, here are my reactants, and here are my products, right? Good. And what happens is we start over here at reactants, and think about our H. Let's use our I2 and H2 issue here. Oh, I'll tell you what. Let's go back to the question. We'll draw this picture over there. Zoink, zoink. We need to draw this energy diagram. Okay, so what I'm going to have is I'm going to have something that looks like here. This is extent of reaction. On this side, I'm going to, right around here, I'm going to have H plus and H2 and I2. And over here, I'm going to have two HIs, okay? And we're going to start, we'll just say, here's my potential energy, and just we pick a point. We're going to start here, and that represents the energy of my H2 and I2. Got it? And then what do we say happens? Hey, somewhere up here, we said that my H's are now separated, and my I's are now separated, right? They're not quite bonded to each other. That shouldn't quite be touching, but they're no longer like this, right? They're no longer with the H's and the I's where they're overlapping. The bonds have been breaking. Well, what did we say is required to break these bonds between the HH and the II? We said energy, so that means we have to put energy into the system, right? Good. And then what happens? I'm going to change colors. What happens after the bonds start forming? Energy is released. Now, how much energy is released? We have to come back up here. Let's look at this. It's a negative value. That means it's exothermic. So what does that mean? Do the reactants have more energy, or do the products have more energy? Well, if it's exothermic, that means the reactants have more energy. That means my starting spot here has to be higher than my ending spot. So I have to come down like that. And so at the end, this represents the energy of my HI. This represents the energy of my I2H2. Got it? And the difference between these represents what? What's the difference between the energy of my I2, H2, and the energy of my two H2s, two HIs? This is my delta H. Got it? So the difference between, we'll put it this way, the difference between my starting point of my reactants and the ending point of my products is the delta H. And in this case, this delta H is a negative value because my energy of my reactants is greater than the energy of my products. Good. Up here, this is what we call the activated complex. Activated complex. Good. And what is an activated complex? You want to make sure we add notes here. Activated complex is the transition between reactants and products at which energy is at a peak or its maximum. The activated complex represents the maximum in potential energy during a reaction. And it's a transitory state. That means it doesn't stay there permanently. So right here is my activated complex. It's the maximum energy. Look at it, it's the highest point on my energy diagram. And then there's one other thing we want to put on here, and that is this thing here. This is my, and we've heard this word before, EA. What is an EA? An EA is my activation energy. Activation energy. Activation energy. And what is the activation energy? It is the minimum energy needed to initiate a reaction. I have to reach this amount of energy or my reaction won't occur. It's a little bit like a roller coaster, right? I don't know if this is a great analogy, but let's say you're on a roller coaster and you get enough energy to get right here. Well, will you go through with the rest of the ride? No, you'll just fall back there. Nothing will happen. That's true about the reaction as well. If I don't have enough energy given to my I2 and H2 to reach this point, the reaction will not occur. Now, once I reach this point, what happens? My I2 and H2 start reforming bonds and I get more energy and my reaction can occur. Woo! So that is an energy diagram. Great. Woo-hoo, I'm glad we're done with that, aren't you? Oh, no, look, we're not. Show on the diagram the effect of adding a catalyst. Yikes. Okay, I have to show on the diagram effect of adding a catalyst. Now, what's a catalyst? Remember, a catalyst does what? It lowers my activation energy. And what is a catalyst? It's something that that lowers my activation energy, but it's not permanently consumed in the reaction. So what do? Do I start at the same spot with the catalyst? Yes, I start at the same spot. Do I end at the same spot with a catalyst? Yes, I end at the same spot. What's the only difference? You have a lower activation energy, meaning my activated complex is at a lower level. So you kind of go like that. Na 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 na. And right here, from here to here, is my activation energy, and we'll put a prime here so that EA prime means catalyzed. Got it? There we go. Notice my delta H is the same, right? And remember, my delta H is the difference between the energy of my products and the energy of my reactants, right? What's my EA? The EA is the difference between my activated complex and the energy of my reactants. Remember, the EA is always from my reactants to my activated complex. Got it? Super. Now, all I need to do is sign this, and we'll take it to New York, and we'll say, hey, it's modern art. Give me $1 million. Good. There we go. You guys try this one and see if you can make some art. Well, let's draw an energy diagram. Zoink, zoink. We're going to put down extent of reaction. I want to put potential energy. I know it starts somewhere. Let's put it right here. What do we have on this side? I have over here carbon, really 2 carbons, and I have H2, right? Good. And I know it ends. Now, My delta H is a positive value. What does that mean? If it's a positive value, remember delta H equals energy of products minus energy of reactants, right? And so if this is a positive value, what does it tell you about the energy of the products relative to the energy of the reactants? It must be what? Greater. So that means it must end, my diagram must end with my products being higher than my reactants. And then we know what? Somewhere in here there's an activated complex, and so it kind of goes like that. What's the difference between where I start and where I end? Right here. What is that? Well, that's going to be my delta H. In this case, that delta H is positive. What's the difference between where I start and my activated complex? That is my activation energy. Here is my activated complex, right? It's the transition state between my reactants and products, and it's my peak of energy. There's the peak of energy. Good. And what else? Show the effect of adding a catalyst. So with a catalyst, what do? Start at the same spot. I go up a little less high, end at the same spot. My delta H is the same. My products are the same. Now, where's my EA? My EA is yoink roughly right here from my reactants to my new activated complex. So this would be my EA prime or EA catalyst, right? We'll say that EA prime equals my catalyzed. All right, good. I know the notes here were a little more all over the board. Sorry about that. A little more, maybe not confusing, not quite as well organized, and I didn't put them in my beautiful concept maps as always, but I think you have an idea of what energy diagrams are all about. Well, that brings a close to our discussion about kinetics and heat. You guys should be able to nail this on the quiz and test. If you have questions, let me know. And that will do it for today. Aloha.